Welcome to this college algebra video on solving systems of equations. Here are some warm-up problems for you to try. The directions are: use a graphing calculator to find the intersection of the following pairs of equations. So take each pair one at a time and try to find the XY coordinates where they would cross. You can pause the video now and try this yourself, or if you're not sure how to do this, I'll lead you through the steps in just a moment. The first thing we need to do is get each of these equations in a form that can go into our graphing calculator. For the first equation, we're going to subtract 3x from both sides to get y equals 5 minus 3x. The second equation, we need to subtract 2x from both sides to get y equals 4 minus 2x. Now each of these is in a form that can be put into the y equals of a graphing calculator. I've put 5 minus 3x into y1 and 4 minus 2x into y2. I typically start with a zoom 6 or zoom standard, a 10 by 10 window, and adjust things from there. Here's the first graph in blue and the second graph in red, and notice that we can see where they are crossing. It looks to me like that intersection point is 1 across and 2 up. But if we're not quite sure what the intersection point is, we can use the graphing calculator features to find the intersection. We start with second trace. In the past, we found a 0, but this time we're looking for an intersection. So we'll choose number 5. The graphing calculator is asking us a question: is y1 the first curve? And even though it's a straight line, the graphing calculator is going to call each of these things a curve. And the answer is yes, so we'll hit enter. Now the graphing calculator asks if y2 is the second curve. Again, the answer is yes, so we hit enter. Finally, the calculator asks us for a guess. We could either just hit enter right now, or we could move our cursor a little closer to that intersection point. If curves cross in more than one place, then you want the cursor to be closer to the intersection that you're interested in. When we hit enter, the calculator will find that intersection point. And the intersection point does turn out to be coordinates 1, 2. What this means is that the pair x equals 1, y equals 2 is the only pair of xy values that will solve both of those equations at the same time. For the next pair of equations, the first equation is already in a form that the graphing calculator can handle, 0.75x minus 4. But the second equation needs to be changed so that y is by itself. We need to add 3x to both sides and then divide by 4. This will give us the equation y equals 5 plus 3x all divided by 4. Now let's put each of these into our graphing calculator. In y1, I put 0.75x minus 4. In y2, I put 5 plus 3x in a parentheses so that we can keep the numerator grouped together, divided by 4. Again, I'm going to start with a zoom 6, and let's see what these graphs look like. These graphs don't appear to intersect at all. But how do I know that the graphs aren't slowly getting close to each other, and perhaps they would cross maybe at x equals 100 or x equals 1,000? Well, I know that these graphs will not ever cross, because if we look back at the original equations, the first graph has a slope of 0.75. The second graph has a slope of 3 over 4, and 0.75 is equal to 3 over 4. Anytime two equations have the same slope, that means those two lines will be parallel. When our two lines are parallel, we will say that there is no solution to this system of equations. There is no xy pair that will solve both equations at once. Finally, let's look at the last pair of equations. We need to get each of them into a form that can be put into the y equals of our calculator. The first equation, we need to subtract 3x and divide by -1. This will give us 2 minus 3x, the entire thing divided by -1. For the second equation, we're going to subtract 9x and divide by -3. That'll give us 6 minus 9x, all divided by -3. When we put each of these into a graphing calculator, we want to use parentheses, set apart the numerator, 2 minus 3x in parentheses, divided by -1. And notice I'm going to use the negative sign at the bottom, -1. For the second equation, start with parentheses, 6 minus 9x, close parentheses for that numerator, divided by -3. Let's see what these graphs look like. Again, I'll start with a zoom 6, standard window, -10 to 10, -10 to 10. Here's the first graph, drawn in blue, and here's the second graph, drawn in red. Now you notice that the second graph completely covered over the first graph. If you don't have a fancy color calculator, it's going to be hard to see this. But here's how I know that these two lines are exactly the same. I can reduce the fraction 6 minus 9x over -3 by dividing top and bottom by 3, and it gets me right back to 2 minus 3x, all divided by -1. Since these are both the same line, we'll say there are infinite solutions. Now, this does not mean that all xy pairs will solve this. Only the xy pairs along that one thin line will solve both equations simultaneously. Our goal in solving systems of equations is to find the solutions of one linear equation and another linear equation. For instance, 5x plus 2y equals 10 and x minus 4y equals 24. Recall that the word "and" in mathematics usually indicates an intersection. We've just seen three ways that lines can interact. One way is that the lines can cross at a single point. Typically, when we see this, we will find that intersection point, and we say that there is one solution to this system. We also saw a pair of lines that was parallel. When we see this, we say that there is no solution. And finally, we saw two lines that covered each other up. One line was drawn directly on top of the other line. When we see this, we say that there are infinite solutions. But graphing is not the only way to solve a system of equations. In fact, for most systems, graphing is going to be sort of a last resort. The graphical technique has some limitations. First of all, if we only have paper and pencil, we have to be very precise in the way we graph. It's not always obvious what the coordinates are of the point where the graphs cross. To get a more exact value, we need to use other methods of solving systems. The two methods that we're going to talk about in this section are substitution, where we solve for a variable and put that expression back into the other equation, and elimination, or some books will call this the addition or linear combination method. This is where we add two equations together to eliminate a variable. Sometimes we have to multiply to get opposites. As we go through the next couple of examples, I'll show you how each of these methods of solving a system of equations can work. Let's start with the system we had on the last page, and we're going to solve this system by substitution. When we're doing substitution, we want to find a single variable in one of the equations that is easiest to get by itself. Now, looking at both equations, I see that the easiest variable to get by itself is going to be the x in the equation on the left. I'm going to add 4y to both sides so that x is by itself. Once I've solved for one of the variables, I like to circle that expression. We're going to put the expression 24 plus 4y in place of x in the other equation. It's not going to replace the 5 or the 2 or the y. It's going to replace x because it's equal to x. If these expressions are very complicated, you want to make sure you use parentheses when you put them into the other equation. So now we have 5 parentheses 24 plus 4y close parentheses plus 2y equals 10. We're going to distribute the 5, collect our like terms, subtract 120 from both sides, and divide both sides by 22. We find that y is equal to -5. but this is only half of the solution to our system. Anytime we have a system of equations with two variables, our solution should have a value for each of those two variables. So we now need a value for x. If only there were some kind of formula that could tell us what x equals. Oh, that's right, it's the formula that I circled. That's why I circled it earlier on, because I knew I would need to use it again. I looked back at x equals 24 plus 4y and replaced the y with a negative 5. This means we're going to take 24 plus negative 20, which equals 4. Now we have both an x value and a y value, and our solution is complete. Let's see how substitution can help us solve an even bigger system. Here is a system of equations with three unknowns. We call it a triangular system because the shape, when arranged in this way, almost looks like a triangle. As I look at this system of equations, there's one variable that I can immediately find the value of. Z has to equal 3 for that last equation to make sense. If I know that Z equals 3, I can put that into the second equation. Here's the substitution part, and I can solve for Y. Add 3 to both sides, divide by 2, and we find that Y equals 5. Now that I know the values for Z and Y, I can substitute those into the top equation to find a value for x. Solve the equation. 3x plus 5 plus 6 equals 8. The solution of this equation is that x is equal to -1. Now I have a complete solution for my system. When I write the solution, I'll write an ordered triple. That is, write the solutions in alphabetical order. -1 first, then 5, then 3. In theory, we could even solve a much larger system of equations as long as it's in that triangular form. This is a system of 7 equations with 7 variables. You can pause the video and try to solve this system yourself, and I'll be sure and post the solution at the very end of this presentation. What we'll find going forward is that problem solving is made much simpler if we can use a technique of solving systems of equations. In the past, when we solved word problems, we often had to get everything in terms of one variable. But now that we can use systems of equations, we're free to use more variables in our problem solving. The key is, if we want to use 2 variables to solve a word problem, we have to look for 2 different relationships among those variables. That'll translate into 2 equations. In fact, in general, the number of equations must equal the number of unknown quantities in the problem if we are to have any hope of getting a single solution. If the number of equations is fewer than the number of variables, the best we can do is to write down some kind of relationship that the variables must have. Let's try solving some word problems now that we have the freedom to use more than one variable. Here's a simple one. The sum of 2 numbers is 33. Their difference is 6. Find the 2 numbers. By the way, with this word problem, I'm going to introduce the method of solving a system by elimination. So as I look at this problem, it's clear that we have 2 different numbers that we're trying to find. Therefore, I'll be using 2 variables. You can choose whatever 2 letters you'd like to represent the variables. I'm going to go with X and Y in this case. And I need to look for 2 relationships between my 2 variables. Well, as I read, it says the sum of 2 numbers is 33. I can write that relationship mathematically, knowing that sum means addition, as X plus Y equals 33. As I continue to read, I get a second relationship. Their difference is 6. So I'm going to take the same 2 variables, difference means subtract. I'll write X minus Y equals 6. I have 2 variables, I have 2 equations, we're ready to solve. Now before I jump right into the elimination method, I do want to give you a little justification for the move I'm about to show you. First of all, let's recall that when you have an equation, One of the properties of equations is that you are allowed to add the same thing to both sides of an equation. That is, I could add 2 to both sides of this equation. That is a legal move. It probably won't help me find a solution. Both sides, x plus y plus 2 and 35, will still have this property of equality. I could also add 10 to both sides of my equation. I'm allowed to do it. It's not really going to help me solve my equation, but I could do it. Now, could I add 10 to one side of the equation and add 5 plus 5 to the other side of the equation? Well, of course, because 10 and 5 plus 5 are the same thing. They're just different ways of writing the same thing. Or could I add 10 to one side and add 5 times 2 to the other side? Of course, because they are both different versions of the number 10. Could I add 10 to one side and add 13 minus 3 to the other side? Again, yes. Could I add 10 to one side and 20 times 3 to the other side? Well, of course, the answer is no in this case, because 10 is not the same as 20 times 3. Let me ask just a couple more. Could I add 6 to one side and 6 to the other side? Of course I could. Could I add 6 to one side and 3 plus 3 to the other side? Of course that's acceptable. Could I add 6 to one side and add 16 minus 10 to the other side? Well, sure, they are still equal. Finally, could I add 6 to one side and add 16 minus 10 to the other side? Of course, because they are both equal. And finally, could I add 6 to one side and x minus y to the other side? Well, it's not clear here that 6 would be the same thing as x minus y, unless perhaps they told us in the problem that 6 was equal to x minus y, and that's exactly what they did in this problem. So what I'm going to wind up doing is adding the second equation plus the first equation. Really what I'm just doing is adding 6 on both sides of the equation, but 6 written in a different way on the left than it's written on the right. So let's use that strategy I just talked about. What we need to do is line up the x's, line up the y's, line up the equal sign, line up the numbers on the other side, and we're ready to go. I'll draw a line under these and add one equation plus the other equation. Add the left sides of these equations, we get 2x, we get 0y, and we get, on the other side of the equal sign, 39. This is the elimination part. We can just write 2x equals 39. We have eliminated the y's. That's where this process gets its name. Now we divide both sides by 2 and find that x equals 19.5. But remember, the question was to find the two numbers. 19.5 is just one of these numbers, so we have some more work before we're done. I can go back to either of the original equations and substitute 19.5 for x. I'll choose the first equation, 19.5 plus y equals 33. Well, subtract 19.5 and we find that y has to equal 13.5. And it's true that if I add these two numbers, I get 33. If I subtract these two numbers, I get 6. So we'll phrase our answer in this way. The larger number is 19.5, the smaller number is 13.5. This next example is going to introduce a little bit more advanced type of elimination. We start with this. If 8 4K Ultra HD discs and 7 Blu-rays cost $337, while 5 4Ks and 11 Blu-rays cost $310, how much does each 4K and Blu-ray cost? Incidentally, I've had to update this example over the years. It used to say Blu-rays versus DVDs. Before that, it said DVDs versus VHS. And before that, it said VHS tapes versus 8mm film strips. And before that, it was CDs versus records. And before that, it was LP records versus 45s. And before that, it was gramophone records versus wax cylinders. I've been doing this example for a long time. But how are we going to solve it? Let's start by assigning variables for our two unknowns. The question at the end says how much does each 4K and Blu-ray cost? So we need a variable to represent 4K and Blu-ray, and specifically, this variable represents how much they cost. It doesn't represent how many discs of each kind. We are already given that. It represents the cost of the discs. I'm going to use K for the cost of a 4K disc and B for the cost of a Blu-ray disc. As I read the first sentence, I see that it says 8 4K discs and 7 Blu-rays cost $337. That's the first relationship that's going to give me an equation. I'll write 8K plus 7B equals 337. On the left side is one way of representing the cost of all the discs. On the right side is another way of representing the cost of all the discs. I continue reading and see that 5 4Ks and 11 Blu-rays cost $310. We'll set this equation up as 5K plus 11B equals 310. Here's where we run into a bit of a problem. If I add one equation to the other equation, like we did in the last example, neither of these variables will cancel out. I'll get 13K, I'll get 18B. Neither one of them is 0. So we have to make some adjustments in order to make one of the variables cancel out. I'm going to choose to make the variable K cancel out, but you could just as easily make the variable B cancel out. Here's how I'm going to do it. I look at the 8K and the 5K, and I want to try to make the numbers in front of K opposite. So I can multiply the top equation times -5. I can multiply the bottom equation times 8. Remember, we're allowed to multiply both sides of an equation by any non-zero number. I'll distribute the -5 through all the terms in the equation and get -40K minus 35B, and -5 times 337 is -1,685. I'll distribute the 8 through the second equation. I get positive 40K plus 88B, and 8 times 310 is 2,480. Now when I add these two equations, the opposite numbers in front of K will cancel each other out. -40K and positive 40K give me 0K. The B's add up to 53B, and 2480 minus 1685 is 975. When we divide both sides by 53, we now have the cost of a Blu-ray disc. A Blu-ray disc would cost $15. Now we'll finish the problem by finding the cost of a 4K disc. We can technically go back to any one of these equations. I'll go back to the 5K plus 11B equals 310, substituting 15 for B. What we get is 5K plus 11 times 15 equals 310, or 5K plus 165 equals 310. Subtract 165 from both sides and divide both sides by 5, and we'll see that the 4K discs cost $29 each. So 4K Ultra HD discs cost $29 each, Blu-rays cost $15 each. A couple of chapters ago, we focused on writing equations of lines. For instance, we'd be given 2 points and have to write the equation of the line that goes through those 2 points. I want to show you a simple method of finding the equation of the line that uses systems of equations. We're going to take the points 5, 5, and -2, -16, and the equation y equals mx plus b, and develop a system of equations. In the first equation, I'm going to substitute 5 for x and 5 for y, and write 5 equals 5m plus b. In the second equation, I'll substitute -2 for x and -16 for y. Remember, the y value comes first here, so -16 equals -2m plus b. What I have now is a system of equations. It's not quite ready to solve yet because I don't have opposite numbers in front of the m or in front of the b. But a quick way to fix that is to multiply the bottom equation times -1. Now we'll have the system of equations 5 equals 5m plus b, and positive 16 equals positive 2m minus b. When I add the equations together, the plus b and the minus b will cancel out. That's the elimination part of this method. And we'll have 21 equals 7m. So our m value is 3. We're halfway to writing this equation of the line. We now know what the slope of the line is. If I substitute 3 back into either of the original equations, I can find a value for b. I'm going to put it in the top equation. 5 equals 5 times 3 plus b. Subtract 15 from both sides, and we have that b equals negative 10. Now we know the equation of our line is y equals 3x minus 10. As our final example, we're going to try to solve a system with 3 variables. We'll use sort of a combination of the elimination method and the substitution method. For convenience, I've labeled each of the equations as equation A, equation B, and equation C. It'll make it easier to refer to these as I'm solving the problem. Well, the first thing I notice in this problem is that I have a positive y in equation C and I have a negative y in equation A. That means if I add equation A and equation C, I should be able to eliminate the y's. And that's what I'll do. Equation A plus equation C gives us 2x plus 5z equals 7. I'll make that my new first equation and leave the second and third equations like they were. The next thing I notice is that if I multiply equation C times negative 2, I'll have a negative 2x to cancel out positive 2x. I'll have a negative 2y to cancel out positive 2y. So that's what I'll do next. Equation A is going to be now that new top equation we had. Equation B is going to stay the same, and equation C is going to be equation B minus 2 times equation C. The x's cancel out, 2x minus 2x. The y's cancel out, 2y minus 2y. The z's are z minus 6z, and the numbers on the other side of the equation are 3 minus 8. Although we don't actually see the triangular shape this time, we can solve this system the way we solved our previous system that had 3 variables. By looking at the bottom equation, I can immediately see that z has to equal 1. Once I know that z is equal to 1, I can go to the top equation and substitute 1 for z, giving me the equation 2x plus 5 equals 7. That solves to x also equaling 1. Finally, now that I know that x is 1 and z is 1, I can go to my middle equation and substitute those values. 2 times 1 plus 2y plus 1 has to equal 3. You should quickly be able to solve this equation and see that y is equal to 0. So we wind up with the ordered triple 1, 0, 1. And in case you worked out that challenge problem earlier, here is the solution to that system. That system had 7 variables and 7 equations. So its solution is written as an ordered septuple, meaning 7 parts. Thank you for watching this video on solving systems of equations. Go out and try some of these problems yourself, and we'll see you next time.